Momentum and pulse, conceptual questions. We have two spacecrafts that are moving together at 50 meters per second, and at some time point they're going to separate. Their mass is designated as m each, and they have an initial velocity of 50 meters per second. We know that no external forces are acting on them, so as long as no external forces are acting on them, their system center of mass will remain at 50 meters per second, something that we're just thinking about. First question, what does it mean when the two-space system is called a closed system? No external forces. A closed system has no external forces acting on it. Assume they're a closed system. What is the velocity of the center of mass after the two spaceships have pushed off of each other? Velocity of center of mass has not changed. It's a closed system. So if you can determine the velocity of center of mass at any time, you can determine the velocity of center of mass at every time. If the spaceship on the left comes to a complete stop, what's the velocity of the spaceship, the other spaceship after the push? So we're going to look at the momentum before, set it to the momentum after, because we're trying to calculate for one of the variables. 2m, which would be the total mass, times 50, the velocity, is equal to m times 0, the momentum of the second one, plus momentum of the other one, the one going to the right, m times v. We get 100m is equal to mv. M's cancel out. 100 meters per second is the velocity. Next, we have a kitten, 3 kilograms, stalking its mother, 8 kilograms. Mother is at rest. Kitten is on the move. The kitten pounces. After the collision, they are stuck together, or they're connected, and they're moving with a combined velocity of 1.4 meters per second. So the whole system is moving at 1.4 meters per second. How fast was the kitten going right before the impact? Let's set up the collision. We're going to say 3 times v, that's 3 kilograms times the velocity of the kitten, plus the momentum of the mother, 8 kilograms times 0, is equal to their combined mass, because they're combined after the collision, they're stuck together, 3 plus 8 times their velocity, 1.4. So on the left, we would have 3v, because 8 times 0 is 0. So 3v is equal to 11 times 1.4, which gives us 15.4. And then we just divide both sides by 3, and we get a velocity of 5.13 meters per second for the velocity of the kitten when he was on the attack. After the impact, what's the velocity of the center of mass? Remember, this is a closed system, so if we know the velocity of center of mass at any point of the system, we know it at every point of the system. And on this one, after the collision, the whole system's moving at 1.4, so we kind of know that's the velocity of center of mass. A student says, there were no external forces here, so the velocity of center of mass was the same both before and after the collision. Do you agree? Yes, absolutely. Newton's first law says an object or a system that is in motion will want to stay in that motion unless acted upon by an unbalanced external force. No unbalanced external forces here, so Newton's first law is going to tell me yes, I agree with the statement. Draw a momentum versus time graph and plot the mother's and kitten's momentum. Well, the kitten had a higher momentum before he hit the mother, then it was slowed down. The mother had no momentum because she wasn't moving, but then she sped up. They had the same velocity at the end, but the mother had more mass, so her overall momentum will be higher. And then when we look at kinetic energy, remember kinetic energy is 1/2 mv squared, where momentum is mv. So the graphs are going to look the same, but now the mass will carry less weight and the velocity will carry much more weight. So I stretched my graph out a little bit, but the look, the pattern, the design of the graph is going to be very much the same. Just the values on the side will be what's different. All right, page 2. Now we've got a collision, 1,200 kilograms going to the right at 3 meters per second, 900 kilograms going to the left, so negative 15 meters per second, and 500 kilograms standing still. What is the net momentum of the system before the collision? Here we're just going to add up all the mass times velocity separately. You don't add up all the masses and then add up all the velocities and then multiply. You mass times velocity plus mass times velocity plus mass times velocity. 1,200 times 3 plus 500 times 0 plus 900 times negative 15. Do not forget that negative. It is important. Direction is important. Velocity is a vector quantity. So we'll say 1,200 times 3 plus 900 times negative 15. Let's put that in a calculator, see what we get. Looks like it's going to come out to negative 9,900 kilograms meters per second because we're multiplying mass times velocity. What's the net momentum of the system after the collision? Were there any external forces acting? Any unbalanced external forces? No. The system was exactly the what it was at the beginning as the end, so the net momentum is the exact same. Draw a momentum versus time graph. Graph all three cars on your graph. So here we're going to need to know the individual momentums before the collision and after the collision in order to graph their momentums. Now we know that their final velocity is going to be something we're going to have to calculate. We don't know their final velocities. Their initial momentums, we calculated that kind of earlier. 1,200 times 3 would be the first one. 500 times 0 would be the second. The green cars or the green truck's initial momentum, and then 900 times negative 15. We can get their initial momentums pretty quickly, but we're going to have to do some calculation to determine what that final combined velocity is, because once they hit, they're stuck together. So we're going to say negative 9,900 is the collective momentum, and that's equal to their combined mass, because the momentum before was the negative 9,900 is equal to the momentum after. Here we know it's a combined mass because they're all stuck together times one collective velocity. So we're going to have to add up their masses, divide it to the other side, and that's going to get us the final velocity for each of those carts. Then we can take that final velocity, multiply by the mass of each individual cart, and know what each individual cart's momentum is, or I'm saying cart, but truck, each individual momentum is for them after the collision. So we've got the after velocity. It looks like it's negative 3.81 meters per second. So they're all moving to the left. For the red truck, the initial momentum, 1,200 times 3 is going to equal, let's get it through the calculator, make sure we get the right numbers. 1,200 times 3 should be 3,600. There we go. And then final momentum will be 1,200 times negative 3.81. Get this through a calculator, make sure that we're accurate as much as possible. Looks like it's negative 4572, so 4,572. Let's do the green one next. The initial momentum of the green, 500 times 0 would be 0. Initial momentum is 0 because he's not moving initially. Final momentum is going to be 500 times negative 3.81. Remember, they all have the same shared final velocity because they're stuck together. So negative 1,905. And then finally the pink truck is going to the left, so 900 times negative 15 for the initial momentum. So negative 13,500. And then the final momentum is going to be 900 times negative 3.81, which would be negative 3,429. So when we draw the graph, the red one's going to start positive and go negative. I have it being as the most negative at the end. The green one's going to start at 0. It's starting at 0, and it's going to drop down to negative 1,905. And I think I misdrew the pink one, because he's going to start at negative 13,500 and go up to negative 3,000. I think I looked at that one wrong. So when you draw the pink one, it should be negative 3,500 going up to a less negative 3,429. So I'll fix that on the key, but just be aware that that pink one was drawn slightly wrong on the before. A student says a baseball batter hitting a ball will give it the baseball greater impulse than the catcher catching the same ball. Do you agree with the statement? Explain your reasoning. So let's think this through. It's asking about impulse. Impulse is J in the formula. That's force times time. It's also a change in momentum. Change in momentum can be calculated as mass times a change in velocity. Well, for the ball, the mass isn't changing, right? The mass is constant whether a catcher catches it or the batter hits the ball. So the mass did not change. So let's look at the change in velocity. Which one will give the ball a greater change in velocity? The batter or the catcher? All right, well, with the batter, without specific numbers, we're just going to have to look at variables, and we're going to have to say that what do we have? The batter is going to have an initial velocity that's, let's say, is positive coming towards them, and then when they hit the ball is going to change directions. So the velocity is going to go from positive v to negative v. Where the catcher is going to have, when he catches the ball is going to go from a positive v to 0 because it's stopping. It's not changing directions. With the batter, it went through 0 going from positive to negative. The catcher, it just goes to 0. So the batter has a larger change in velocity. If the mass is the same, but the velocity has a larger change with the batter because it's going from towards him to away from him, where the catcher just simply stops it, we agree. We agree with what the student is saying, that the batter has a greater impulse because of that larger change in velocity. So yes, we agree. And all that work there, we'll count that as our explanation. Brings us to number 5, the very last question on the page. Teenager standing on top of a frictionless ice, checking his text messages. One of these texts is a message from his mother telling him to clean his room. This infuriates him, so he throws the iPhone as far away as it can. Assume the floor is greasy and is frictionless. Well, he was standing on ice, so yeah, I guess so. Which of the following has changed? The net momentum. Did the net momentum change? No, because there's no external forces. No unbalanced external forces, so the net momentum did not change. The position of the iPhone teenager's system center of mass. Was there any external unbalanced external forces? No, so the center of mass isn't going to change. The velocity of the iPhone, yes, it was standing still. It was not moving in his hand, and then it was moving, so the velocity of the iPhone did change. The momentum of the teenager, yeah, when he threw the iPhone with a positive momentum, he slid back with a negative momentum, so his momentum changed. And then the kinetic energy of the system wasn't moving, and now it is. And kinetic energy is only positive, so there was an increase in kinetic energy from nothing to something.